All right. So we begin this chapter with a very interesting question. What is the difference between science and technology? Anybody? Kanan? Probably, yeah. What else? Raise your hand. Raise your hand. Yes.
Wow, technology is a result from, or like a.
Okay, I think you can say that. Yes. Give me an example of a difference between technology and science. Yes. Okay, I think I can agree with that. Kanan.
So technology is like a mechanism that allows you to open and close a door, and science is the study that allows the production of that mechanism.
Okay, good. Elaine. Yeah, I could agree with that as well. Anybody else? Raymond.
Kind of on a loop, like science makes technology and technology makes science.
Okay, I can kind of see that under certain circumstances. That needs to be around your neck, sir. Christian. Okay. All right, let me give you the ultimate example. So what if Danielle becomes an ornithologist? What's an ornithologist? Study of birds. So she becomes an ornithologist. Actually, her specialty, ever since she was a little girl, she was enraptured by raptors. We're talking the carnivorous ones, the hawks, the falcons. So she becomes an ornithologist and with a specialty in raptors. Okay, so she studies them. She studies videos of them flying, and she's especially intrigued, because they'll just kind of glide for a little while, and then they see a prey. And have you seen them? They tuck their wings in, and they go straight down. Yeah, that's what I'm talking about. They tuck their wings in. It's really they form a really interesting shape, and then they plummet. And right before they hit the ground, right as they're coming right next to their prey, they'll unfurl their wings, grab the prey, and start flying. Okay, so she writes, after months and months of studying this from different angles, different vantage points, using a specialized camera, she writes a paper in which she writes in detail, okay, what exactly is going on, how that peregrine falcon can actually descend so quickly that the rabbit doesn't even know what hit him, even though that falcon may have been 70, 80 yards away in the air. All right. So, wow. So she gets published, and other ornithologists happen to read it. But what she doesn't know is that Robert Hill is by this time an aerospace engineer. Okay. And he has a special interest in falcons for one particular reason. His job, he works for the Air Force, and his job is to design new fighter planes. So he reads Danielle's work, and he goes, this is very interesting. I wonder if we can apply this. And he starts toying around with the idea of wings that can retract when diving, and then come back when pulling out. And of course, we're talking about something that probably happened close to 50 years ago, with the F-15, because up until the F-15, probably all our fighter planes were fixed wing. That means the wings just, they vibrated like. That scares me about riding on an airplane and seeing the wings do this kind of stuff. When you realize you're in an aluminum tube with wings that do this, and we're perfectly fine with that. We're watching videos, we're listening to our music, and we don't have any problems with being an aluminum tube with wings that do this. Anyway, up until that time, you could only go so fast when you were dive bombing, or when you were going after another fighter who was also diving. You could only go so fast, and that was because our wings were fixed. Because if you went too fast, what would happen to the wings? Break off. They would fly off. All right. So he thought to himself, I wonder if I can apply what a Falcon does. And so that's how the F-15 was developed. They were no longer fixed. They could be tucked in, and that means when that F-15 dive bombs, it can go really, really fast. Okay, so give me somebody using that analogy. What is the difference between science and technology? So and probably knowing some naturalists the way I do, Danielle was probably mortified when she found out what Robert used her research for. Okay, but what is Danielle's job as a naturalist, as an ornithologist? She just wants to expand human knowledge of birds. That's it. I mean, we are insatiably curious. We love to know things. She wanted to let the whole world know a little bit more about how eagles and falcons and hawks hunt. Okay? But what did Robert do? He took that science and he applied it and created a device that imitated that. Okay. Well, what happens is this. Not necessarily in this example, but in many examples, Robert would, based on Danielle, would create the technology that makes money. And because it makes money, then what he would do is he would go, and they said, okay, so this is the money that you need to invest. And he would go and call up, hi, Miss Rose, this is Robert Hill. I'm an aerospace engineer, and I'm really intrigued in your research with the Falcons. I would like to give you a grant for further research. So you're right. It is like, I think it was Raymond who talked about it. It is a circle because Robert made a lot of money from his invention. What is he going to do? He's going to turn around and basically pay Danielle to do more. Okay, study more. Let me learn more from you. And that's because the fact is Danielle's research going to make money? No. So that's the problem with pure science. With pure science, you've got to make money. So the only way that pure science makes money is when people, engineers, take that pure science and apply it to technology. Now, let me give you a challenge for those of you who are thinking about going into engineering and those of you who are thinking about going into science. Okay, people need to keep studying a very intriguing animal called a brittle star. And these are like sea stars, but they have really thin legs with little spines on them. Do you know what I'm talking about? I mean, they look... Yeah, they've got like a little disc in the middle, and from the disc, you have usually 5 arms. But the crazy thing about those arms is that they can do anything, move in any direction. Okay, the only problem is that all you have is one little nerve going down the top and one little nerve going down the bottom, and somehow that is able, we can't even move our fingers like that. Somehow that is able to make the 5 arms go in any direction. Okay, those of you who watched, I think it was the second Spider-Man movie with Dr. Octopus. You know, he had his arms that he was able. Okay, we don't have that. We do not know how to make robot arms that can move in all the directions that a brittle star legs can move. But the thing is, you would think it would be easy because it's one little nerve and one little nerve, and then it's just a bunch of muscles. But it is so complex that we can't even recreate it. So, technology and science are related, and you guys have all explored. You've done a good job. This is what I had to say. Science is the process of gathering, analyzing, organizing knowledge about the natural world. Okay, those of you who talked about the door. Yeah, that's physics. You realize there's a lot of physics involved in just opening a door. Okay, but you can also be an engineer that knows nothing about the physics. You learn what it needs, needs to happen. You need hinges, so you engineer the hinges. You engineer the latch. You engineer the handle, and all of a sudden the door opens. Okay, but you first had to have physicists that help us understand what exactly has to happen for that door to work. Technology is the application of the science converting natural resources into goods and services. In other words, technology helps us make money. And then money turns around and helps to pay for the science, because science typically doesn't make money. When we use up erasers on our pencils or gasoline in our cars, are they disappearing? No, the atoms are rearranging themselves to form new things that may or may not be usable. Okay? Except for my wife. My wife does something very strange. Think about it. When you go to bed, okay, let's say that you weigh yourself before you go to bed. Okay? So you spend all night breathing. At the very least, you're breathing. That's muscular effort. So you're taking in oxygen, breathing out carbon dioxide. The process of breathing actually releases more mass than if you're not breathing. So all night long, my wife is burning glucose, which is a nice large molecule, and oxygen, which is gas, and converting it to 2 gases that she expels out: water vapor and carbon dioxide. Okay? So in theory, every time you wake up, you should weigh a little bit less. Except for my wife, who seems to gain weight. I lose weight from one of the last things that I do before I go to bed, because I'm on a diet, is I weigh myself. When I wake up, I am usually a pound to maybe 1.5 pounds lighter. Okay, it's okay because I gain it over the day. But my wife gains weight. I don't know how. I don't know if little creatures go inside her mouth and die inside her body. Because think about it, is there any new mass coming into her body overnight? You would think that she's losing carbon dioxide and water and it's all going out. No, she gains weight. I don't know. I've already told her it's impossible, but no, yes. I know, I wonder about that. She sleepwalks and yes. So what does it mean to use something up? It usually is changing the resources. For example, my wife and all of us, we take glucose, which is a type of sugar, and we react it with oxygen to form carbon dioxide and water. It's all there. All the atoms are there, but we're rearranging them. Okay, so we're not using up sugar. We're just converting it into carbon dioxide and water. So, what is the chemical equation that describes, for example, the burning of coal? Now we're in number 1. That is, carbon plus oxygen forms carbon dioxide.
So what is with the S and the G?
Okay, good. I'm adding a little bit of information here to help you visualize what exactly is going on. The S stands for solid. So it's coal. So it's a piece of solid, a solid coal, solid carbon. The G stands for gas. G, dude, if it was G, it would be jazz. It's not jazz, it's gas. Okay, so are you driving yet? One of these days you're going to be driving, you're going to go to an intersection where there's a light. What, you wait for the light to turn green so that you can Joe? No, you wait for the light to turn green so that you can go. I'm being consistent. The letter is G. The letter is G. How many girls are here as opposed to boys? Marina. Oh, I was just talking about it. Okay, thanks. Okay, no, it's not girls, it's girls. G. G. Okay, the whole G thing is actually, we can take the French for that. That's all right, Kanan. Apparently, you must have, this whole G thing must have mixed you up because you're needing in student affairs. Okay, probably you'll be back. Can't imagine that you did something so horribly wrong that you actually are in trouble for it. All right, so remember Lavoisier, the guy who said you can't destroy anything, you can't create anything, you can just rearrange it. Look at this equation. Does it obey Lavoisier's law? Yeah, why? How many carbons do you have on the left before? How many carbons do you have on the right after? How many oxygens do you have on the left before? How many oxygens do you have on the right? Okay, so this equation obeys Lavoisier's law of conservation of mass. I don't eat till 11 o'clock. I mean, till lunchtime, and then after lunch, I just snack on them. It'll take me 2 or 3 weeks to get through this pack. All right, so what is the chemical equation for describing the rusting of copper? Jot this one down. Cu solid plus O2 G yields Cu2O solid. I'm sorry, I left out the solid there. Why don't you add that? Add the S. All right, now, would Tony be happy with this equation? Why not, Jasmine? What? How many coppers do you have on the left? How many coppers do you have on the right? Ooh, Tony says, I don't like. How many coppers on the left? How many coppers on the right? Ooh, how did oxygen end up getting destroyed? Oh, no, no, no. We've got a problem here. You've got a problem. Things have to add up. Things have to add up. All right. Target number one. If given a chemical name or formula for a chemical equation, I can correctly balance it. Because the problem is Tony can't be unhappy. Tony must be unhappy. What is the law? Must be happy. What is the law of conservation of matter state? Who proposed it? Remember, it was Tony Lavoisier. Matter cannot be created or destroyed. It can only change forms. In other words, all the atoms you begin with, you must end up with. Does the last equation obey this law? No. How do we fix an equation so that it can conform to the law? Well, what we're going to do is we're going to have multiples of it. We're going to add a coefficient. It's called a big number to the beginning of each type of molecule until everything equals out. It's almost like a puzzle. If we puzzle it out and equal it out on both sides, we say that the equation is balanced. The equation is balanced. All right, copy this down and then you're done. And tomorrow, we will do examples of this, and I'll probably give you plenty of homework, plenty of time to do your homework. One. All right, so here we go. Let's balance. Ray, clickers. All right, so let me show you how easy this is. It is like playing a game of some sort. It's almost like a math game. What you need to do is make sure that you keep Antonio Lavoisier happy. And how you do that is by making sure you have the same number of positives and negatives on either side. All right. You ready, Joey?
Yes. No.
How many fingers do you have? Oh, that's more than good enough. All right, so how many sodiums do you have on the left? Count them. Use your fingers. 1. Good. Now, on your other hand, how many sodiums do you have there? Okay, so you should have 1 finger on. Okay, good. Yes. Goal. Okay, how many eyes do you have on the left? Okay, so put out 2 fingers. How many eyes do you have on the right? Oh, no, we only have 1. So you can't go around and change the formula NaI because the formula NaI is perfect. So your only choice is to multiply the whole thing, NaI, by something that gives you eyes, 2 eyes. So what can you multiply NaI by that will give you 2 eyes? Brilliant. Okay, now we have now fixed the eyes. Yeah. Congratulations. Now, the rule is, once you're done, always go back to the beginning and check everything because sometimes in your zeal to fix something, you may have messed up something that was previously fixed. All right, so get your fingers up again. How many sodiums? And how many sodiums? 2. Oh, so we have 2 sodiums over here. We need to have 2 sodiums over here. So what do we multiply sodium by in order to have 2? How about eyes? Eyes are still good? 2 eyes and 2 eyes. All right. For which one? Oh, okay. So what do we put here? An understood 1. If there is nothing there, that means there's a 1 there. Okay? You can't have a 0 because then that would mean you have no iodides. And then you have 2 iodides on the right. You can't have a 0. Blanks are understood 1s. No? All right. AC. How many Ks? How many Ks? Yay! How many CLs? How many CLs? Yay! How many O's? Ruh-roh. What's the problem with 3s? They're odd numbers. What was the rule that we went over? If you encounter an odd number, it may be difficult to balance on the other side, so we usually multiply by 2. But let's see if that is the case. How many O's? Okay, is there going to be any way that we can ever get 3 to equal 2? No. Okay, so what are we going to, we're going to have to multiply KClO3 by something in order to make it into an even number. AC, what do we multiply it by in order to make it an even number? Yes. Okay, so now how many oxygens? And here? Okay. Now remember, Cassidy, in our zeal to fix something, we may have unfixed something. So, did we? How many Ks? AC, how many Ks? Ruh-roh. Now how many Ks? How many CLs? How many CLs? All right. Zacharias. How many Ks? How many Ks? Fix it. How many PO4s? Remember what I said in the rules. As much as possible, keep the polyatomic ions together. That way you don't have to worry about how many P's, how many O's. Just think of it as PO4 as one thing. How many PO4s? How many PO4s? Okay. How many H's? How many H's? How many H's? What? We'll fix it. How many CLs? How many CLs? Okay, let's go back and check. How many Ks? How many Ks? How many PO4s? How many PO4s? How many H's? How many Ks? I'm sorry, how many H's? How many H's? How many CLs? How many CLs? All right, Cassidy. Well, you were talking, so I figured that this was so easy that you had a chance to talk. So how many C's? How many C's? Fix it. How many H's? How many H's? That's not enough. So what would you multiply by in order to get 8? How many O's? Be careful with these combustion reactions, Crazy E. Why? Because oftentimes the O's are spread out over 2 formulas. So you got to keep track of them. All right, Cassidy, how many O's? How many O's there? How many O's here? What is 6 plus 4? What times 2 is 10? All right, good job. Let's fix it. Let's make sure we've not messed anything up. How many C's? How many C's? How many H's? 4 times 2 is? 5 times 2 is? 3 times 2 is? Plus 4 times 1 is? 6 plus 4 is 10. Good job. Now, this isn't hard. It's just trial and error. So what I'm going to do is I'm going to give you plenty of trial so that you can have plenty of opportunities to error. So we're done.